Welcome back everyone. In today's video, I will be discussing the concept of the moles. So we're going back in time a little bit here. This is a very, very old idea that was first proposed in 1810, which is much earlier than the idea of isotopes or the use of mass spectrometry. So what is a mole? Now, there are multiple definitions of the word mole, but we're not talking about the furry animal or the spot on your face. In chemistry, a mole is a unit measuring a specific number of things. Okay, so a unit measuring a specific number of things. And you should have seen a few examples of a unit measuring a specific number of things in the past in your everyday life. So I'm just going to give you a few examples here. So a pair is a unit measuring two things. A brace apparently is also two things. I've never used this word before. A dozen is 12 because dozen's 13, and then you have a score, you can have a gross or a myriad. So these words, pair, brace, dozen, and so on, are examples of units measuring specific number of things. So if you have 3 pairs, that means that you actually have 6 things in there. And if you have 4 dozen, it means you actually have 48 things. So in this vein, a mole is really similar. It is also a unit measuring specific number of things. It's just that the number of things that is in a mole is a lot bigger than what you normally see in like a pair or dozen. So a mole is equivalent to this many things. So around 602 billion trillion things. So it's a massive number. How many pairs of zeros? I'm not even going to do the counting here. So for ease of practice, this number, this many things, is normally written using scientific notation. So we'll normally write it as 6.02 times 10 to the 23 things, or 602 billion trillion things. So a lot of things. So you can say 1 mole is equivalent to 6.02 times 10 to the 23 things. If I have 2 moles, it means I have twice that amount of things. Okay, this particular number is also referred to as Avogadro's number or Avogadro's constant. I think I'm going to call it Avogadro's constant just to highlight the fact that it is a constant, which means that it will never change. And it is named after Italian scientist Avogadro, who I think this is the only portrait of him and he did not look very happy in it. This is why you should always smile in any photo that is taken of you, because it may be the only surviving photo and then people may think that you actually never smile. He also has a really dark shadows face that he sleep. Anyway, so it was named after him even though he actually didn't discover this number. So Avogadro constant is 6.02 times 10 to the 23, and it is the number of things that is in 1 mole. So this is a very, very big number, 602 billion trillion, and people have had a lot of fun trying to think of thought experiments. What if you have a mole of moles? This is in a What If book, if anyone has it or have heard of it. So what would happen if you were to gather a mole? So if you gather 6.02 times 10 to the 23 of the furry animals in one place, that was the question. And then people did the calculation, and essentially if you have that many moles, the furry animal, in one place, it's going to form a planet that is bigger than the moon. So this is a massive number. If you have that many moles, if you have 602 billion trillion moles, the animal, it is a massive amount. So anyway, so what if you have something smaller? What if you have a mole of donut? Like, we had way too much time. I think who did this calculation? If you have a mole of donut, somebody did the calculation, it would cover the entire Earth in a donut layer 18 kilometer deep. So if you have 602 billion trillion donuts, you're going to have a layer of donut around the Earth. So again, it is a massive number. That's a lot of donuts. Let's think of something smaller. I remember this example because the first time I learned mole was in Vietnam, and it's an Asian science textbook. Of course, the example that they use is how much is a mole of rice. But I remember that example still. I thought it made an impression on me. So how much is a mole of rice grain? And you would think, oh, rice is really small. So 602 billion trillion grains of rice cannot be that much, right? Well, apparently it is a lot. A mole of rice grains would cover the land area of the earth to a depth of about 75 meter. And then somebody, and I remember this from my old year 8 science textbook. A mole of rice grains is more grains than all the grain that has been grown since the beginning of time. So again, it is a massive number, even with something as small as rice. If you have a mole of rice, that is still a lot of rice. That's more rice than we have ever seen. But anyway, I sound like Donald Trump. Um, Last question. What if I have a mole of water molecules? So what if you pick something that is truly very small, like water molecules? If I have 602 billion trillion water molecules, how much water would that be? Is it going to be all the water we have ever seen? Not quite. If you have a mole of water molecules, that's about 18 mil, 18 grams. That's about 18 mil of water. So the reason why we have to use a number so big, like the mole or 602 billion trillion, is because the things that we are dealing with in chemistry are really, really small. So you need a lot of it for it to be even, of some significance. So a mole of water is only around 18 ml water, exactly 18 grams. But so it's actually not a lot. It's like about a third of a cup of water. I drank more water than that this morning. Okay, so that's essentially the reason why we need to use a number that big, is because the things we're dealing with in chemistry, atoms, molecules, are so small that you need that much in order to even see it. There is another specific reason why we settle with that number, and I'll talk about that in the next video, not this one. So anyway, what we need to be able to do is to convert between the number of mole and the number of atoms or molecules or particles. So I'm just going to start with this example, and for all questions today, we're going to leave our final answer correct to 3 significant figures. So first question, how many atoms of aluminium is in 1 mole of aluminium? I think everyone can answer this question quite easily. If you know that 1 mole is 6.02 times 10 to the 23 things, then 1 mole of aluminium is the same as 6.02. And the only reason why we use the scientific notation is because we want to save time, and then quite frankly, nobody has enough time to write 23 zeros every single time there's a question like this. So you can just write 1 mole of aluminium is 6.02 times 10 to the 23 atom of aluminium, which I think works out to be around 27 grams of aluminium. So it's not even that much in grams anyway. It's a lot of atoms. Okay. So that's, I don't know what, okay, I know what happened there. So that's the answer. Now let's look at example 2, because chemistry is so easy. How many atoms of aluminium is in 2 mole of aluminium atoms? So if you know that 1 mole of aluminium atoms is 6.02 times 10 to the 23, all you need to do here is 1 mole, so 2 mole of aluminium atom. All I need to do is just to double 6.02 times 10 to the 23. And then I'm going to, okay, I really shouldn't be using. So 12.04 times 10 to the 23. And if you want to use actual scientific notation, then it's, of aluminium, or that equals to 1.204 times 10 to the 24. So I just move the one of the 10 to here. So you have this. Okay. I think I may want to point out one thing, but maybe I'll do that later. Hang on. Times 10 to the 23. Yeah. Okay. I'll talk about the E notation in the calculator later. So if you look at this example, essentially there are a few different concepts that are being used here. So we're just gonna use some letters to represent different concepts. So the first thing, which I already told you, which is Avogadro's constant, this is the number of particles of things in 1 mole. Now there is a symbol for it. This is not the official scientific symbol, but this is the one I'm going to use just to make it easier. So the symbol here is Na, so Avogadro's number or Avogadro's constant. And the unit, you can think of it as particle per mole, and the value is 6.02 times 10 to the 23. So Na is constant. There is another symbol that we're going to use from now on, and that is a symbol N to represent the number of moles of a substance. And the unit is mol. So it's mole, but just you drop the E. This is a scientific notation. We're going to use this a lot from now on, so start getting used to it. So lowercase n always means the number of mole. Just to make life even more confusing, there is another symbol for the number of particles, and that is uppercase N. So the unit would be particles, or depending on the question, could be atoms, ions, molecules, and we'll look at a few examples later. So what I'm going to do is I'm just going to go back to this question that I just did, and I'm just going to use the symbols that I just defined. So how many atoms of aluminium? So this is the question, how many atoms of aluminium? So what the question is asking for is the number of particles. In this particular case, the number of atoms. So the unknown, which is number of atom, can be rewritten using symbols as capital N. So number of particles is capital N. And I'm just going to be a little bit more specific and say that I'm trying to find the number of aluminium atoms. So this is the unknown. And the information that is given to you in the question is that you know that there are 2 moles of aluminium atoms. So 2 moles. So you're given the number of moles. So you're given lowercase n of aluminium. I know this question is very easy. There's no need to convert into symbols, but you're going to need to be able to use the symbols when the questions get more complicated. So this is just to practice using the symbols really. So the information given is the number of mole of aluminium. So lowercase n of aluminium is 2. And you have to use Avogadro's constant in this question, even though it is not given in the question. So Avogadro's constant is going to be assumed knowledge. I will give you the value for all assessments, so you don't have to actually memorize it, but you need to know that you have to use it. So we always know that Na, or Avogadro's constant, which is the number of things in 1 mole, is 6.02 times 10 to the 23. Okay, normally we don't put a unit here, but you can if you want. In this case, going to be atoms per mole. So the actual calculation here is that N of Al is number of mole times Avogadro's constant, if you will. And then from there, you get the final answer. So this is, you can think of this as the mathematical relationship between the number of particles, the number of mole, and Avogadro's constant. So if we linking everything together, then there is the first way, well, this is the second way, to link everything together is you could use this little triangle. I don't know whether you've used it in the past, but anything that's on the same row, basically you can multiply them together. So this triangle means that if you multiply the number of mole and the number of and the Avogadro's constant together, you will get the number of particles. And I think the way to use a triangle as well is whatever you need to find, so whatever your unknown is, you just need to cover it, and then whatever is left is what you need to use to find the unknown. So let's say for example 2, I want to find the number of atoms. So if I cover that, then basically I get this, which means that I need to multiply the number of mole with Avogadro's constant. So this is to find capital N. Or if you want to find the number of mole, then if you cover that, you basically will have something like this. So you're going to have N over Na. So it shows you that the number of mole is going to be equal to the number of particles divided by Avogadro's constant. So the triangle is one way that you can use to summarize the relationship between the number of particles, the number of mole, and Avogadro's constant. The other way is what I use. Actually, no, I don't really use this. But it can be used when the questions get more difficult, and that is using conversion factor. And it is really just the same thing. So conversion factor, it is just the same thing, but it's a different representation of the triangle. So the conversion factor is basically, in this case, Avogadro's constant. So Avogadro's constant, which is 6.02 times 10 to the 23 things in a mole, you can think of this as a ratio between the number of particles and the number of mole. So from here, I can create a ratio so that the number of particles over the number of mole is the same as 6.02 times 10 to the 23 over 1, because this is the number of things in 1 mole. So this ratio, this is your conversion factor. So this is the conversion. So the difference between this representation and the triangle is that this one uses ratio and the fraction a little bit more. I do recommend, you don't have to use this method or the other method or any method for this, because these questions are fairly simple, but I do recommend using this because later on when we get to semester 2, there will be quite a few questions, and even in year 12, quite a few questions when we're going to use the conversion factor to convert from one thing to another. So this is things in 1 mole. Okay, so from now on, I'm going to stick with this method for doing the question, but you can always use the triangle as well. Okay, let's try one more question. Actually, I think we have 15 examples today, so we have many questions to try. So example 3, how many water molecules are in 0.464 mole of water? Before we start anything, it is a very good idea to try to convert the words to the actual letters. So how many water molecules is the question. This is my unknown. This is what I need to find. So the unknown, if I translate it to the letters, it's going to be capital N. I wanted to find the number of molecules. So capital N is number of particles, and depends on the question. It could be number of atoms, number of ions, number of molecules, so on and so forth. In this case, it is number of molecules, water molecules. So I'm basically trying to find capital N of H2O. That's my unknown. It is a very good idea to get into the habit of summarizing the questions, especially if you don't know where to begin. I know some of you will be able to do this in 2 seconds, but when you're stuck, start by summarizing the question. So how many water molecules are in 0.464 mole? So the information that is given for me here is the number of mole, which is small n, of water, and that is 0.464 mole. Now, obviously, you also are allowed to use Avogadro's constant, which is 6.02 times 10 to the 23, even though it is not explicitly given in the question, it is assumed that you can use it. So if I want to use this, basically, I'm going to create a ratio between unknown and given. Okay, so the unknown is N of H2O. The given, I already know the number of mole, and that is 0.464. And this unknown of a given ratio is going to equal to 6.02 times 10 to the 23 over 1, which is the conversion factor that we just created earlier. And then from here, if I move the 0.464 to the other side, I should be able to find the answer. This is just, if you understand if you understand the question mathematically, you can use whatever method you want. I just need to stick to one method, and a lot of you may think, oh, this is really long for a very simple question, and that's fine. It's just I'm going to use this method later when the question actually gets complicated, so I just kind of want to make things a little bit consistent, which is why it looks like I'm writing a lot for a very simple question. But anyway, if you can use another method, feel free to do that. Just make sure you show working out if the question is worth more than a mark. Okay, so the answer correct to 3 significant figures will be 2.79 times 10 to the 23. And let's box the final answer. I don't think I forgot to do that for the previous question, and molecules is the unit. Okay, so that's example 3. Do we have example 4? Yep, example 4. How many moles of water are in this many molecules of water? Okay, so example 4, let's start again by summarizing the question. Example 4 asks you to find the number of mole of water. So the unknown in this case is the number of mole of water. That's the unknown. The information given, so this question is just the opposite of example 3. You're actually given the number of molecules, so you're given capital N of water, and it is 6.80 times 10 to the 45 molecules. And of course, you also are allowed to use Avogadro's constant, which is 6.02 times 10 to the 23. So once again, I'm going to use the conversion factor to answer this question. So unknown over given. So the unknown in this case is actually the number of mole of H2O, and the amount given is 6.80 times 10 to the 45. So because the number of mole is now the numerator, I need to flip my conversion factor. So if we go back to the original conversion factor, this is a conversion factor, but this ratio only works is if n is on top, capital N is on top and lowercase n is at the bottom. But you can flip the conversion factor. It really depends on what your unknown is. Normally, we just put the unknown on the numerator just to make it a little bit easier for you to transpose. So either of these should work. In this question, because number of mole is my unknown, I'm going to use the reciprocal version of the conversion factor. So I'm going to go with 1 over 6.02 times 10 to the 23. So that 1 and the number of mole are on the same level, and the number of things are on the same level. And then from here, you can transpose to answer the question. So you just have 6.80 times 10 to the 45 over 6.02 times 10 to the 23. When you're doing this calculation in the calculator, just make sure that you use brackets if you have to. So I do recommend, especially if you can't create the fraction expression on the calculator, make sure that you use bracket. So the division actually happens to both of these and not one. If your answer turned out to be 10 to the power of like 68, you've done something wrong. So if you don't get the answer that you're supposed to get, maybe just check the calculator again. A lot of the times mistakes happen because people just input the wrong thing into the calculator, which I think I just did. So why is it still so big? It is still very big. This is a ridiculous amount of mole. But anyway, that's fine. It is actually, you're right, the 6.8 times 10 to the 45 is really big. Okay, so 1.13 times 10 to the 22 mole. Okay, moving on. Oh, that's it. For now, let's just box the final answer. By the way, this is very unlikely. It is extremely unlikely that you're going to find a number of mole this big, but I guess it's possible. How many liter of water would this be? Times 0. Yeah, it's a really big number, that's all. But anyway, if we follow the maths, that's the final answer. Very unlikely to happen, but I just realized that I think I may have made a typo here. But anyway, that's the answer for question example 4.